There is a particular kind of failure that does not appear in any of the famous photographs of the Second World War. It does not generate dramatic newsreel footage. It does not produce statues or memorials. It does not get mentioned in the memoirs of generals or the speeches of presidents. It is one of the most consequential failures of the entire industrial war, and almost nobody outside of aircraft mechanics and metallurgists has ever heard about it. The failure happened thousands of feet above the ground, inside the cylinder of an aircraft engine, where a small piece of fired ceramic was supposed to be holding back 60,000 volts of electrical potential, while simultaneously surviving temperatures above 600 degrees Celsius and the chemical violence of leaded aviation fuel exploding several times per second. When the ceramic failed, when it cracked or eroded or fouled or simply stopped insulating, the spark plug stopped sparking, the cylinder stopped firing, the engine lost power, and in the air over the Atlantic or the Pacific or the Mediterranean, the airplane that had been built by tens of thousands of workers and was carrying 10 human beings on a mission that mattered now had a problem that no amount of training or courage could solve. Aircraft engines in 1941 had a lot of spark plugs. A B-17 Flying Fortress had 4 engines, each with 18 cylinders, each with 2 spark plugs, 144 spark plugs per aircraft. A B-24 Liberator was similar. A naval Wildcat or Hellcat fighter, 14 cylinders, 28 plugs per aircraft. Across the entire wartime American air fleet of more than 300,000 aircraft, the number of spark plugs in service was in the tens of millions, and every one of them depended on a small piece of ceramic to do its job. By 1942, German pilots flying the latest Daimler-Benz engines were reporting reliability problems severe enough that the Luftwaffe had to reduce the boost pressure of the DB-605 from 1.42 atmospheres down to 1.3 atmospheres, sacrificing power until, among other things, improved spark plugs became available in late 1943. Soviet mechanics maintaining the engines of British-supplied Hurricanes and American P-39 Airacobras kept careful records of which spark plugs lasted how long. The British RZ-5 plugs in a Merlin engine lasted 50 to 60 hours, and the Soviet mechanics noted this as a remarkable indicator of quality. Inside captured German factories at the end of the war, Allied investigators found that German spark plug production had never quite caught up to the demands of high-altitude, high-boost combat operations. The American plugs lasted longer, they failed less often, they tolerated more abuse, and the reason was a piece of ceramic refined over a decade in factories in Flint, Michigan and Toledo, Ohio that almost nobody outside the industry has ever heard of. This is the story of that ceramic, the company that perfected it, and the asymmetric advantage that it quietly delivered to one side of the air war. To understand why the ceramic mattered, you first have to understand what was happening physically inside the cylinder of a wartime aircraft engine. The combustion chamber of a Wright R-2600 radial engine, the kind that powered the TBM Avenger torpedo bomber, the B-25 Mitchell, and a dozen other American military aircraft, was approximately the volume of a large coffee can. Inside that volume, several times per second, a mixture of gasoline vapor and compressed air was being ignited by an electric spark, producing a chemical explosion that drove the piston down with enough force to deliver something on the order of 1,500 horsepower from a single 14-cylinder engine. The temperatures inside the cylinder at the peak of combustion exceeded 2,000 degrees Celsius. The pressures exceeded 1,000 pounds per square inch. The spark plug was screwed into the wall of this cylinder. Half of it sat in the relatively cool exterior environment of the engine cowling, half of it sat exposed to the full violence of the combustion chamber. Down the middle of the plug ran a metal electrode carrying high-voltage electrical current, at the moment of spark somewhere between 15,000 and 40,000 volts, in the most demanding aircraft installations as high as 60,000 volts. That electrode was separated from the metal body of the plug by a piece of fired ceramic. The ceramic had to do three things at once, perfectly, hundreds of times per minute for hundreds of hours of operation. It had to insulate. 60,000 volts of electrical potential, given the slightest path to ground that did not pass through the intended spark gap, would simply leak through the ceramic instead of jumping the gap in the combustion chamber. A leaky plug did not spark properly. An engine with leaky plugs lost power and ran rough. It had to seal. The pressure and temperature of combustion would push hot combustion gases past any opening, no matter how small. If the ceramic cracked, hot gases would escape through the crack, eroding everything in their path and potentially blowtorching their way through engine components. And it had to do all of this while being attacked, chemically, by the byproducts of leaded gasoline combustion. Tetraethyl lead, which had been added to aviation fuel since the late 1920s to prevent engine knock, decomposed in the combustion chamber into lead oxide compounds that deposited themselves on every available surface, including the ceramic surface of the spark plug. Lead deposits on the plug created alternative conductive paths around the intended spark gap. Within enough flying hours, a lead-fouled plug stopped working entirely. This was the engineering problem. It was solvable. It was just not easily solvable, and the countries whose factories solved it best got an advantage that propagated outward into every air engagement of the war. From most of the early 20th century, the standard insulating material in aircraft spark plugs was mica. Not the laboratory-grade transparent mica that physics students use to look at thin film interference patterns, but the thicker, layered mica that could be stacked, compressed, and used as a robust electrical insulator. Aircraft spark plugs through the 1920s and into the 1930s used insulators made of stacked mica washers compressed under tension by the central electrode itself, with mica's natural cleavage planes oriented to prevent electrical breakdown. Mica worked. It was, for its era, a reasonable engineering compromise. It was relatively cheap. It was relatively easy to assemble. It tolerated heat reasonably well. It was elastic enough that small movements in the metal parts of the plug did not crack the insulator. It also had a fatal flaw, which became apparent in the 1930s when aviation fuel began to be routinely leaded. Lead deposits accumulated on the mica surfaces. The mica was layered, with microscopic gaps between the individual sheets. Lead oxide compounds, deposited from combustion, worked their way into those gaps. Each flying hour, more lead. Each maintenance interval, the gaps were a little more contaminated. Eventually, the conductive path through the mica became as easy as the spark gap itself, and the plug failed in a way that was difficult to detect from the cockpit because the engine still ran, just not as well, and the loss of power was gradual. For peacetime aviation, this was an inconvenience. Mechanics cleaned the plugs at regular intervals, replaced the worst ones, and the aircraft kept flying. For wartime aviation, where engines were being pushed to higher boost pressures, higher fuel octane ratings, and higher continuous power outputs than any civilian aircraft had ever required, the mica plug became a liability that could be measured in lost combat hours. The same problem had been recognized in Germany. Siemens, the German electrical giant, had begun work on an alternative material in the late 1920s, a sintered ceramic made primarily of aluminum oxide, also known as alumina, fired at temperatures above 1600 degrees Celsius to produce a dense, hard, electrically insulating solid with melting point of around 2000 degrees Celsius. The basic chemistry was straightforward. The manufacturing was not. Alumina is one of the hardest materials in industrial use, second only to diamond on most practical hardness scales. Forming it into the complex shape of a spark plug insulator, firing it without cracking, glazing the surface for resistance to surface tracking, and doing all of this at production scale was an industrial process that took years to perfect. The Germans had the patents. They had the science. What they did not have by 1939 was the production capacity to make aluminum-insulated spark plugs in the quantities a major war would require, and they had spent the rearmament years committed to a series of design changes that prevented their factories from settling into the long, patient industrial rhythm that ceramic mass production required. The Americans did, and what the Americans did with their head start changed the air war. The AC Spark Plug Company was founded on October 26, 1908 by a French-born American bicycle racer and engineer named Albert Champion in partnership with William C. Durant, the founder of General Motors. Champion had previously founded the Champion Ignition Company but had departed it after a dispute with his original partners. The new company, AC, took its name from the founders' initials. By 1925, before it formally became a division of General Motors, AC had bought a plant on Dort Highway in Flint, Michigan, and was producing spark plugs at automotive scale for the rapidly growing American automobile industry. Albert Champion himself had founded a separate company, the Champion Spark Plug Company, headquartered in Toledo, Ohio, that became AC's main domestic competitor. Through the 1920s and 1930s, both firms refined the design and manufacture of spark plugs for an automotive market that was growing at 20% a year. Engines were becoming higher compression, fuels were becoming higher octane, ignition systems were becoming more demanding. The American spark plug industry, driven by the competitive pressure of selling into the big three automakers, was forced to keep refining its products at a pace that no other national spark plug industry could match. The ceramic insulator was the core technical challenge. Through the 1930s, both AC and Champion were investing heavily in alumina-ceramic technology, improving the purity of the raw alumina powder, refining the sintering process, learning how to glaze the surface for resistance to electrical tracking, and figuring out how to do all of this at the volumes required for tens of millions of plugs per year. By the late 1930s, the American firms had matched or exceeded the original German technical lead in alumina-ceramic spark plug technology, and they had something the German producers did not: integrated automotive-scale production capacity. Hundreds of thousands of plugs per month, millions per year, manufactured by trained workers operating purpose-built machinery on production lines that had been refined through a decade of civilian competition. When the war came, this capacity pivoted. The AC Spark Plug Division of General Motors won the Army-Navy E Award 5 times during the war, a recognition for excellence in war production. The original award was presented on September 2, 1942, with the first additional star added in June 1943. Demand for aviation plugs grew so rapidly that AC ran out of space in its Flint facility and had to set up additional spark plug production in a borrowed Fisher body plant in Ionia, Michigan, which itself won the Army-Navy E Award twice. The Ionia plant, originally designed to build automobile bodies, found itself producing millions of aircraft spark plugs for engines whose specifications it had not existed to support 5 years earlier. The Champion Spark Plug Company, separately, was running its own wartime production in Toledo, Ohio, with similar levels of output. Between the two of them, plus smaller producers like Bendix Scintilla, which made the BG aviation plug, the American spark plug industry was building tens of millions of aviation plugs by 1943, and most of them shared a common technical denominator: a high-purity sintered alumina ceramic insulator that German and Japanese producers could match in quality but not in quantity, and that Soviet producers could match in neither. To grasp the scale of the spark plug problem, it helps to do the multiplication. A B-17 Flying Fortress had 4 Wright R-1820 cyclones, each with 9 cylinders, each cylinder with 2 spark plugs, 72 plugs per airplane. A B-24 Liberator had 4 Pratt & Whitney R-1830 Twin Wasps, each with 14 cylinders, each with 2 plugs, 112 plugs per airplane. A B-29 Superfortress had 4 Wright 3350 Duplex Cyclones, each with 18 cylinders, each with 2 plugs, 144 plugs per airplane. A naval Avenger torpedo bomber had a single Wright 2600 with 14 cylinders and 2 plugs each, 28 plugs per aircraft. The United States built approximately 300,000 aircraft during the Second World War. The average aircraft carried somewhere on the order of 50 to 60 spark plugs at any given moment. The total fleet had, at any given time, something like 15 to 20 million spark plugs in service. Each of those plugs had a finite life. A standard aircraft plug in routine wartime operation lasted, depending on the engine, the operating conditions, and the maintenance practices, somewhere between 50 and 250 flying hours before it had to be cleaned or replaced. Lead fouling, electrode erosion, ceramic damage, thermal shock, any of these could shorten the operational life of an individual plug. Across an aircraft fleet that was logging millions of flying hours per month at peak, the consumption of spark plugs was enormous. AC alone was producing millions of aviation plugs per year, and even that was not enough, which is why AC had to expand production into a borrowed Fisher body plant in Ionia. The economic logic worked out to something simple. Every airplane needed spark plugs to fly. Every flight consumed some fraction of a plug's life. Every combat mission, every long-range bomber raid, every transit flight across the Pacific or across the Atlantic was effectively burning down a stockpile of small ceramic cylinders manufactured in Michigan and Ohio. If the stockpile ran out, or if the plugs in service started failing at higher rates than the supply could replace them, aircraft would be grounded. The American supply did not run out. The German supply for many of the plug types required by the latest high-boost engines did. The Soviet supply was so chronically insufficient that Soviet air crews kept careful, almost reverential records of how many hours their British-supplied or American-supplied plugs would last, because the difference between a plug that lasted 50 hours and one that lasted 20 determined how many missions the aircraft could fly between maintenance stops. This is the kind of statistic that does not appear in the standard accounts of the air war. It is the kind of statistic that operates entirely below the level of generals and pilots and tactical engagements. It sits inside the engine cowling, doing its work silently until it stops working, at which point the aircraft starts losing power and the pilot starts making decisions that he would not have had to make if the small piece of ceramic at the end of his spark plug had been built 2,000 miles away in a factory that had been refining the same product for 30 years. There is one further multiplication worth doing. Every plug that wore out had to be replaced. Every aircraft that returned from a mission carried with it a quiet maintenance debt, some fraction of the operational life of each of its plugs consumed during the flight, drawn down against a stockpile that was being replenished every day by trains arriving at air-based supply depots with crates of fresh AC and Champion and Bendix Centil plugs. The supply chain that made this possible ran from bauxite mines in Arkansas, through alumina refineries, through the ceramic forming and firing plants in Michigan and Ohio, through electrode fabrication shops, through assembly lines, through Army and Navy depot warehouses, all the way to a mechanic standing on a tarmac in the Aleutians or Tunisia or New Guinea with a torque wrench and a fresh plug in his hand. Every link in that chain had to keep working. Across the war, it did. The German aircraft industry of 1942 was not, by any reasonable measure, technologically inferior to the American aircraft industry. German aero engines were sophisticated and powerful. The Daimler-Benz DB605, the BMW 801, the Junkers Jumo 213, the experimental Jumo 222, these were engines that, on paper, were the equal of anything the Allies were fielding. They produced competitive horsepower. They were assembled with characteristic German precision. They were flown by some of the most skilled air crews in the war. What they had, increasingly, were reliability problems, and a disproportionate share of those problems traced back to the ignition system. The DB605 was the engine that powered the Messerschmitt Bf-109G, the most produced variant of the most produced German fighter of the war. When the DB605 entered service in 1942, it was supposed to deliver 1.42 atmospheres of boost pressure. By 1943, problems with reliability, including spark plug failures, piston damage, and lubrication issues, had forced the Luftwaffe to derate the engine. Boost pressure was reduced to 1.3 atmospheres. Horsepower was reduced correspondingly. The Bf-109G, designed to outperform the Spitfire at the altitudes where the air war was actually being fought, was now flying with less power than it had been designed to deliver. The restriction was not lifted until late 1943, when, among other improvements, better spark plugs became available. The Jumo 222, a flagship aircraft engine intended to power the Junkers Ju-288 strategic bomber, ran into similar problems. During the 100-hour type test of the A/B1 variant in April 1941, the engine showed spark plug damage after 60 hours of operation. The test also revealed problems with the injection pump and camshaft bearings, and the Jumo 222 never reached operational service in sufficient numbers to matter. But the spark plug failure mode was the kind of recurring detail that, multiplied across the German aero engine industry, was bleeding capacity from the Luftwaffe in ways that the standard tactical histories rarely capture. There's an architectural reason for the German shortfall, and it traces back to the industrial choices Germany had made in the 1930s. German precision manufacturing was extraordinary at low volumes. It was extraordinary at producing one perfect example of a complex component. What it was not optimized for, in the same way American manufacturing was producing millions of nearly identical units to a tight specification with workers who had been trained in months rather than years. The American spark plug industry had spent the 1920s and 1930s learning, by competing for automotive contracts, how to mass-produce aluminous ceramic insulators at automotive volumes. The German spark plug industry had been producing high-quality plugs in modest quantities for an aircraft market that the Luftwaffe was now demanding be expanded by an order of magnitude. The problem compounded. As the war went on, German skilled labor was conscripted in increasing numbers, even by 1944, from the engine factories themselves. The Daimler-Benz engine test stands in Stuttgart had to halt operations at points in 1944 because there were no technicians available to staff them. Hundreds of soldiers were eventually pulled back from the front and reassigned to their original factory positions. Among the casualties of this manpower crisis was the German ceramic spark plug industry, which had needed steady investment and patient industrial development at exactly the moment when its skilled workforce was being sent to die in Russia. The Americans, 3,000 miles away, were doing the opposite, drafting unskilled workers into factories where the production processes had already been engineered to require minimal training, and where the spark plug insulators were being formed, fired, glazed, and assembled by people who had been at their machines for only a few weeks. The most poignant evidence of how much the spark plug supply mattered comes from Soviet maintenance records. When the United Kingdom shipped Hurricanes to the Soviet Union in 1941 and 1942 under Lend-Lease, the aircraft arrived with their full ignition systems, including their Rolls-Royce Merlin engines and their British RZ-5 spark plugs. Soviet mechanics, accustomed to dealing with chronic shortages of every kind of spare part, kept careful records of which components from the British aircraft outlasted Soviet equivalents. The Merlin engine itself drew mixed reviews. Some pilots complained about its altitude performance. Some praised its smoothness. The mechanics, who actually had to keep the engines running, focused on a different metric entirely. The RZ-5 spark plugs, according to Soviet maintenance reports, lasted 50 to 60 hours of operation. The mechanics noted this with what one historian has described as an almost reverential tone. 50 to 60 hours was, by Soviet standards, an extraordinary lifetime for an aircraft component. Soviet-manufactured plugs in Soviet-manufactured engines often lasted half as long or less. The British plugs were one of the small daily things, like good machined tolerances, or properly hardened bearings, or properly sealed bushings, that gave Allied aircraft an advantage that Soviet maintenance crews could measure in hours of operation per spare part. The American P-39 Airacobras supplied to the Soviet Union told a similar story from a different direction. The P-39 had reliability problems with its Allison engine. Early war Allisons had a particularly short service life, sometimes failing in fewer than 50 hours. But the spark plugs in those engines, when they were the American-manufactured plugs, generally outlasted the bearings, the Allison bearings, the supercharger, and most of the rest of the engine. When a P-39 Airacobra had to be pulled from frontline service for engine repair, it was rarely because the spark plugs had failed. It was because the rest of the engine had failed around plugs that were still functional. This is not the kind of fact that the Soviet propaganda apparatus emphasized. The official narrative of the air war was about Soviet pilots in Soviet aircraft fighting Soviet engagements. The reality, recorded in the maintenance logs of frontline units, was that a meaningful share of the Soviet air capability was being delivered by Western components, and within those components, the small ceramic insulated objects that ignited the fuel-air mixture in the cylinders were a chronic supply-side advantage that Soviet industries simply could not replicate at scale. The same pattern, in reverse, governed the Allied bomber campaign over Germany. A B-17 over Schweinfurt or Regensburg had 144 plugs in its 4 engines. If even a handful of them had failed at the wrong moment, if an engine had lost enough cylinders to its plugs that required feathering during a mission, the bomber would have fallen out of formation, become an easy target for German fighters, and likely been lost. The fact that B-17 plug failure was rare enough not to be a major operational concern was again the product of the small ceramic in the insulator of each plug doing its job under conditions that would have broken any inferior product. The 8th Air Force did not write home about the spark plug supply. They wrote home about the fighter escort, the flak, the navigation, the weather. But the spark plug supply was working in the background of every mission they flew. One of the things that makes the spark plug ceramic story illuminating is that it cannot be reproduced quickly. It is not, in the technical sense, a complicated material. Alumina is one of the most abundant industrial ceramics in the world. The basic process, taking high-purity alumina powder, blending it with small percentages of other oxides like magnesia and silica, forming it into the shape of an insulator, firing it at high temperature and glazing the surface, is the kind of thing that a competent industrial chemist can describe in a paragraph. The challenge is doing it consistently, at scale, with workers who do not have decades of accumulated experience. The American spark plug industry by 1942 had been doing this for more than 30 years. Inside the Flint and Toledo and Ionia plants, there were workers who had been operating sintering kilns since the early 20s. There were ceramic engineers who knew, by experience, what each batch of incoming alumina powder would behave like in the firing process, and how to adjust the temperature ramp accordingly. There were tooling specialists who knew exactly what wear profile a forming die would develop after 1,000,000 units, and when to replace it. None of this knowledge could be written down in a manual and transferred to a German or Soviet factory in less than years. The same logic applied to the entire supply chain that fed the spark plug industry. The alumina ore came from refineries, many of them in Arkansas, where the bauxite deposits had been producing aluminum since the early 1900s. The magnesia and silica additives came from established mineral suppliers. The metal components of the plug, the threaded steel shells, the central electrodes, and the gaskets came from precision metalworking firms that had been refining the same parts for decades. The glassware that sealed the ceramic to the metal came from specialized glass producers like Corning, which had spent the same period developing the kind of glass-to-metal seals that would survive thermal cycling. The whole ecosystem, taken together, was an industrial body of accumulated expertise that no individual factory, however well-equipped, could replicate from scratch. When the war came, this ecosystem expanded but did not transform. The same companies kept making the same kinds of components, just at higher volumes for new customers. The same workers kept doing the same kinds of work. The same engineers kept refining the same kinds of processes.
The transition from making spark plugs for Chevrolet engines to making spark plugs for Wright Cyclones required adjustments. Different sizes, different operating temperatures, different specifications, but it did not require reinventing the industry. The industry was already there. This was the structural advantage that Germany could not, in the time available, close. Even after Albert Speer rationalized German aircraft engine production in 1943 and 1944, even after German engineers solved many of the specific technical problems with the DB605 and other engines, the underlying ceramic spark plug industry remained a bottleneck. The German producers could make plugs that, at their best, were the technical equal of the American product. They could not make as many of them, or as consistently, or with the same labor profile. And in a war that was being fought across millions of flying hours per month, the difference between technical equality and industrial superiority was the difference between holding the air and losing it. There is one more dimension worth noticing. The spark plug industry was, throughout this period, almost entirely civilian-owned and operated. AC was a division of General Motors. Champion was an independent Toledo firm. Bendix Scintilla was a New Jersey supplier. The federal government did not, in any direct sense, run any of these companies. What the government did was guarantee orders, provide materials, and create the demand. The actual manufacturing, the engineering decisions, the quality control, the labor management happened inside private firms that had been doing this work for decades. The result was an industrial output that the planned economies of the totalitarian states could not match, because the planned economies had not had the patient pre-war commercial development that had built the American industry in the first place.
There is a thought experiment worth attempting at the end of this story. Imagine that you are an American spark plug, manufactured by AC in Flint, Michigan, in the spring of 1943. You have an alumina-ceramic insulator formed under hydraulic pressure from a precisely blended powder, fired in a kiln at over 1,600 degrees Celsius, glazed for surface resistance, and assembled with a nickel alloy electrode and a steel shell. You weigh about 30 grams. You are roughly 2.5 inches long. Your manufacturing cost, in 1943 dollars, is probably less than $2. You are one of 300 or 400 million similar plugs that AC alone is going to produce over the course of the war. You are shipped from Michigan to a naval air station in California. You are installed in cylinder number 12 of a Wright R2600 engine on a TBM Avenger torpedo bomber. The Avenger is loaded onto an aircraft carrier. The carrier sails to the Western Pacific. The Avenger is launched from the deck on a mission against a Japanese transport convoy. During the mission, you fire some 6,500 times. You survive every firing. You return to the carrier. You sit through several days of waiting, and on the next mission, you fire 6,000 more times. You keep firing. You keep insulating. You keep sealing. You keep refusing to crack. After 50 or 100 or 200 flying hours, a maintenance crew removes you from the engine. They inspect you. They clean the lead deposits off your ceramic surface. They check the electrode gap. They either reinstall you for another tour or replace you with a fresh plug. Either way, you have done the job. The pilot of the Avenger has, throughout your service life, never once had to think about you. He has thought about the enemy fighters, the flak, the navigation, the weather, the survival of his crew. He has not thought about whether his spark plugs were going to insulate the next time he advanced the throttle. He has taken your reliability for granted. This is what it looks like when an industrial supply chain works. The product disappears into the background of the operation it supports. The fact that it is working is invisible. The fact that it is not failing is invisible. The decades of accumulated industrial expertise that produced it are invisible. Only when the product fails,
Only when a German engine has to be derated because of spark plug problems, or a Soviet maintenance crew has to record the precise number of hours a British spark plug lasted before it stopped working, does the importance of the small ceramic object at the end of the ignition wire become visible at all.
The American victory in the air war was the product of many things: pilot training, aircraft design, tactical doctrine, industrial capacity, strategic bombing, long-range escort fighters. The B-17, the B-24, the B-29, the P-47, the P-51. All of these things mattered. None of them would have mattered if the engines had not been running. And the engines would not have been running mission after mission, year after year, if the small ceramic insulators inside their spark plugs had not been doing their job. Invisibly, consistently, in numbers no German or Soviet industry could match. When you look at the cultivated narrative of the Second World War, the heroes are the visible ones. The pilots in their flying jackets, the generals at their maps, the president at his microphone, the engineers in their laboratories, the Rosie the Riveter on her assembly line. These were the people whose work was photographed, filmed, and celebrated, and rightly so. The hero of this particular story, the small ceramic cylinder in the AC or Champion or Bendix spark plug that propelled tens of millions of cylinder firings without dramatic failure, has no statue, no memorial, no anniversary day. It existed only to do its job and then be replaced by another one exactly like it. It came out of a factory in Flint or Toledo or Ionia and ended its life in a maintenance bin in Saipan or Bari or East Anglia. Nobody outside the industry remembered its name. But the wars of the 20th century, and almost certainly the wars of the 21st, are decided by exactly this kind of object. The unglamorous component, mass-produced by patient industries that nobody photographs, doing its job under conditions that would destroy almost any other product, propelling capabilities that the strategists and the generals get the credit for. If you want to understand how the air war was actually won, look at the spark plug. Look at the small piece of fired ceramic at the end of the ignition wire and ask yourself how many of those tiny pieces of alumina, in factories nobody now remembers, kept the engines running through the decades-shaping campaigns whose names everyone still knows. What other invisible components do you think have quietly decided wars or industries in our own time? Leave a comment below, and if you have a family member who worked at AC, Champion, Bendix, or any of the other arsenal of democracy supplier factories, share their story. The people who made the components that made the engines run deserve to be remembered, even if the components themselves never were.